All right, assume that the level of a certain hormone in the blood of a patient varies with time. Yeah. Suppose that the time rate of change, derivative, right? Time rate of change, the derivative is the difference of two terms, okay? Yeah. Between the first one, sinusoidal input, yeah, some function related to sine function, okay, yeah, all right, input of a 24-hour period from the thyroid gland and a continuous removal rate, removal, you take out, remove the thing, proportional to the level present, Y function. And Y function is the hormone level at T, Y of T. Proportional, there is a constant, proportional. Set up a model for the hormone level in the blood and find its general solution. Find the particular solution satisfying a suitable initial condition. All right. So the question. So we need to do the modeling. Set up equation. Because the law is given. Okay. So the physical law is given in the problem description. Here, let me draw the physical law. Suppose that. So after this, suppose that. That's the given physical law. Okay, time rate change, difference, input, and gland removal rate proportional. This is the physical law part. So we set up equation based on this given physical law. Okay? All right. The hormone level, we use Y function. Our usual Y of T to represent the hormone level. All right. Then, so let us write the equation explicitly. Term by term. All right. Y of T, hormone level at time T, interpretation. Interpretation, that physical law, given physical law. Okay, all right. Sinusoidal input. We need a function, right? A general. So what's that function? Sinusoidal. Sine of some angle. Sine of some angle. Here we use A plus B cosine. We know sine and cosine the same shape, right? Sine and cosine has the same shape. The difference is the shift is different, right? So we can adjust the capital A and capital B to match, all the, sine function at any location. So we can use this general expression, capital A and capital B, the cosine. So you may argue, why you use cosine, you do not use sine here. Probably for some convenience. I mean, if you change sign, also okay. Also okay. But when you take a derivative, when you take an integral, there is some, slightly different things. But it's not a big deal. It's not a big deal. All right. Here, there is a 24-hour period. So we need to interpret this part. What's the 24-hour period? But because your sinusoidal function, sine function has a period, right? Sine function has a period. Sine function is a periodic function. Periodic function, there is a period. So here, the given information you need to use, it tells you the period of the sinusoidal function is 24 hours. Okay? 24 hours. Because what is this omega, right? This omega is another constant you use to adjust period, right? Yeah. With different omega, you have different period, right? Yeah. So here, you need to determine for what omega you have 24-hour period. So you need to determine omega first. Yeah. For what omega, you get a 24-hour period. Yeah. First, we need to determine that omega. Yeah. All right. Yeah. Yeah. First, let's recall. So what is a periodic function? What is the periodic function by definition? Okay. If f function is periodic with certain period, f function is periodic with certain period. Okay. All right. So f function x plus period, usually we use t, okay, equals f of x. Okay, yeah. And the period, usually this t we use the, minimum period. Yeah. Because when t is a period, 2t is also period, right? 3t also period. Any integer multiple of t also period. But we want to take the minimum. Okay? Yeah. Otherwise, you have so many different periods, right? Yeah. So when we talk about, we always work on the minimum, smallest period. Yeah. Yeah. All right. So here, yeah, 24 hours. Yeah. That is the smallest period. Okay. Yeah. All right. Then let's calculate omega. Yeah, because we want to calculate omega. Yeah. All right. 24-hour period. Yeah. So now, cosine theta function equals sine theta plus pi over 2. Yeah. Okay. Yeah. So sine, cosine, just the difference is a shift. Okay. Yeah. So angle shift. So the shape exactly the same. Yeah. And the period also the same. Sine function, cosine function, both 2 pi period. 2 pi period. All right. Now, we want to look at sine or cosine omega t plus 2 pi equals itself, right? Yeah. So if you look at that, okay, yeah. Cosine omega t equals cosine omega t plus 2 pi, right? Yeah. Yeah. Okay. Yeah. Omega. Yeah. By the 2 pi period property. Okay. 2 pi period property. All right. Then, but the omega t plus 2 pi, we can factor that omega out because omega is constant. Omega is constant. Can we write the expression inside the parenthesis as factor omega out? Omega times big parallel parenthesis t plus a constant. 2 pi over omega. Right? We factor omega out. Okay? Yeah. Now, after you write in this form, t plus this extra constant part, that is the period. Okay? Yeah. Yeah. Compared to our f of x plus t. Okay? Yeah. X corresponds to t. Yeah. So this corresponds to capital T. Okay? So the period is 2 pi over omega. Okay? The period is 2 pi over omega t. All right? And it tells us the period is 24 hours. That means 2 pi over omega equals 24. So you can find omega, right? Omega equals pi over 12. Pi over 12. Yeah. So then, omega is known. Yeah. Omega is known. Yeah. So only two unknown constant, capital A, capital B. Yeah. Yeah. These two constants, based on the real world application. Real world application, you should have the capital A, capital B. Okay, should be given. Yeah. All right. So then, now we need to set up an equation. We need to write the ODE. Yeah. All right. Removal rate. Yeah. Because in the representation there is a removal rate. Continuous removal rate proportional to the. No. Because the hormone removal. Yeah. So losing. Yeah. Reducing the hormone. Yeah. In what rate? So that's the removal rate. Yeah. Because, removal. Yeah. So that's the minus term. Yeah. Minus, smaller, becomes, the hormone level becomes smaller. Yeah. So the minus term. So that minus term, removal rate proportional to the level present. Yeah. Yeah. Y of t. Yeah. Level present. Yeah. Because proportional, when you say proportional, you should have a constant. Yeah. Positive constant, K. K. Proportional. Okay? Proportional. Yeah, positive. Yeah. Yeah. If it's negative, then it's not removal, right? Like increasing. Yeah. So removal minus a positive term. Minus a positive term. That's removal. Okay? So capital K is positive. Yeah. Positive constant, capital K, then the present. Level present, Y of t, level present. Okay? So this removal rate, this should be minus this K times Y of t. The removal, all right? Representation. Then we are ready to write the final ODE. Yeah. All right. Yeah. The final ODE. So here, let's recall the mixing problem. Yeah. Our mixing problem, yeah, the situation is similar. Yeah. Right? Yeah. The water tank, yeah, the mixture, the brine, you add a inflow, outflow, right? So inflow, yeah, just like here, you add the hormone, right? The sinusoidal input, that's the inflow, right? Sinusoidal input, that's the inflow. Yeah. Removal rate, that's the outflow, right? Outflow of that mixing problem. So here we can do analogy from our mixing problem. Our mixing problem has a balance law. So here we have a similar balance law, okay? Yeah, because something flows in and flows out should be balanced. The rate in, out, change should be balanced. Yeah, so that's the balance law, all right? All right, Y of t. Y of t, the rate of change. Yeah, the hormone rate of change equals balance law, salt inflow rate. Here, the sinusoidal input. That's the inflow rate. Then salt outflow rate, that is the removal rate. Okay, that's the removal rate. So the pattern, the format, the same. So we use the same pattern, same format. Yeah. We can treat as a generalized balance law, right? Generalized version of balance law. Okay? Yeah? Because the hormone, should satisfy certain balance property, right? Yeah. So we can, do analogy to that balance law. Yeah. All right. So Y prime, Y prime equals the positive rate, yeah? So you add, sinusoidal, yeah? Because you add the hormone level. So it's positive, right? The rate. Then removal rate minus Ky, okay? Minus Ky. Yeah. So this is the ODE we need to solve. Okay? That is the ODE we need to solve. Yeah. We just discussed how to solve this type of ODE. Yeah. So we can plug in the formula. Yeah. So because we have the final formula. Okay. So we just apply our final formula to find the solution. Yeah. All right. So here, let me work a little bit. Okay. Yeah. I I may not work completely, but let me work the first few steps to show you some points. All right, now we need to solve this ODE. Yeah. So it is the pattern we just discussed, P of x, R of x, right? Yeah. But so here I want to solve a simplified version. Yeah. Yeah. Otherwise, if we keep A, B, K, then the formula will be very complicated. Okay? Very messy, very complicated. Our textbook uses that K, A, B, K version. So you can see the formula is very long. Okay? Yeah. So if you want to take a look. But here, because we just want to apply the formula, solution formula, right? So we want to make our life easier. So let's use A, B, K, all equal a simple case. Then let's solve this equation. Okay? Yeah. Solve that equation. Yeah. Because we have a formula for this general ODE. Yeah. To do that, we need to calculate the H function. Yeah. H function here, the P is 1. Yeah. So the H function should be very simple, right? H function. Yeah. Then the Y function is like this. Yeah. After you find the H function, then you can write the Y function in this form. Yeah. The R function, this is the R function. Okay? Yeah. So let me just write a few steps. Okay? Write a few steps. Yeah. First, H function is easy to write. Yeah. But our H, it's a function of t. Yeah. So 1 dt equals t. We do not use constant here. No. Why? The reason is we only need to find one h, right? One integrating factor. One h, we want to pick the simplest h. We don't want to add any constant to make it harder, right? Yeah. So for the single function, we only take the easiest one. Yeah. Then the y of t should have e to the negative h, e to the negative t, integral r function 1 plus cosine pi t over 12, r function times e to the t, dt. Okay? Then plus c, some constant c, e to the negative t. Right? Yeah. So here you can see, in order to find the y function, you need to calculate that integral. If you can calculate that integral, then you are done. Okay? Yeah. So here, let me just focus on that integral part. Yeah. All right. For that integral part, we can split it into two integrals. The first one is simple, e t dt, plus the second, a little harder, okay, cosine. Okay, yeah. The question is how to calculate this integral. Yeah, the first one trivial. Okay, so first one e to the t. Okay, yeah, e to the t. That's simple. Yeah, so e to the t. You don't worry about it. But the only question is how to calculate the second one. Yeah. You have a cosine term, you have e term. It's a product of these two terms. Yeah. Yeah. Integration by parts, right? Yeah. So here, you need to use the, in this situation, you need to do the integration by parts. Right? Yeah. So you need to determine u and v, right? Yeah. That's standard way. So here I just, remind you. Yeah. You need to the integration by parts. So we only work on this part. DET. Yeah, I wrote in this way, but based on my experience last year, many students, they didn't feel comfortable writing this way because they want to write the UV. They want to write explicitly U is what function. V is, yeah, it's okay. Yeah, U is your favorite way. But for me, if I do the, so you have U dV, right? UV, yeah. So then you do the integration by parts. Yeah. So it's fine. You use your favorite way. Because many students, they do not feel comfortable on using differentials. Yeah. I use differentials a lot. Okay? Yeah. Yeah. But so U times V, okay? Yeah. Cosine pi t over 12, U times V, et, okay? Minus V du, okay? Du derivative, d cosine pi t, you need to take derivative, okay? Du, yeah. So then, simplify it. But here, the reason I want to show you this kind of detail is because after you do integration by parts once, you cannot get it because you get a sign, right? So you need to do second time. Do integration by parts twice because second time you go from sine to cosine again. Okay, so you have now you can find the cosine integral of the cosine expression. Okay, so here I won't complete. So I just want to let you know you need to apply integration by parts twice. Twice integration by parts. Okay. Yeah. If once, still, you cannot find the answer. Yeah. So you need to do second time, then you can find the answer. Okay? Yeah. Because in our textbook, the integration by parts intermediate steps, skip it. Yeah. So you just see the final formula, a long, messy formula. How to get that? Okay? So here I use a simple example to show you how to get that final answer. Yeah. Yeah. All right, so we finish this example. Yeah. Let's move to the next topic. Yeah. So we have, second Bernoulli equation. Yeah. A special type of ODE. Yeah. But first you need to check if the pattern must be right. When the pattern is right, there is a smart solution. Bernoulli discovered it. Okay. A smart way to find a solution. Yeah. So it's very interesting. Yeah. All right. So let's look at the Bernoulli equation. Yeah. Bernoulli equation has this form. See, P, that right hand side slightly different. Okay. G of x times y to the a power. That special. Okay. Special term. Y to the a. Yeah. A. So what is that a? You may ask what a is any real number. So that's the Bernoulli equation. See? Yeah? Very special. Yeah. But the solution is very, very nice. The structure. Yeah. Structure is very nice. Yeah. All right. So let's take. So first, before we work on the Bernoulli equation, let's look at the cases. Yeah. The simpler cases. Yeah. We already have them, simpler cases. A equals 0, so that's the one we just solved, right? Yeah? P of x, R of x. Yeah? We have that formula. So A equals 0, we're done. Okay? We're done. So, yeah. A equals 1, it's homogeneous equation, right? A equals 1, so we have homogeneous equation. And it's separable, we can also solve it, right? It's a separable ODE. So A equals 1, yeah. We have the solution already. Okay? Yeah. All right. Then we need to consider the case A not equal to 0 and A not equal to 1. And it is a nonlinear form in this case, nonlinear. Remember how we define the linear? Because with respect to y, it is not linear. Y to the a. So this time, this term breaks the linearity, right? Y to the a, this term breaks the linearity property. All right. Yeah. But the solution, yeah, so Bernoulli gave us a special form of the solution. You just introduce a new variable u. U has the form y to the 1 minus a. This special form, okay? Then, after cancellation, simplification, you will get our old familiar ODE form. We can solve. We know how to solve old familiar form. All right? All right. Let's take a derivative by chain rule. U prime by chain rule equals parenthesis 1 minus a times y to the negative a. Yeah. That's the power rule, right? Yeah, that's the power rule. Okay? Y to the negative a. So because minus 1. That 1 is gone. Okay? Yeah. Then by chain rule, multiply y prime. Chain rule. Okay? All right. Now you plug in. Yeah. Oh, before you plug in, because you want to write y prime equals certain representation. Y prime. Okay? Yeah. All right. Then, now you plug in. Yeah. Because y to the a can be yeah. Yeah. To the a. Yeah. So not cancel out. Yeah. But yeah. Yeah. Simplify like this. Okay? All right. Then another step, simplification. Yeah. So y is gone, you only have u function. Y is gone. Okay? Yeah. Y is gone. Okay? Yeah. Because here, yeah, y is gone. Yeah. The nice thing is, this is just the u, right? By assumption. So then, after simplification, yeah, all y terms can be represented as u terms. So then you have a new equation for u function, and it's a first order ODE, and we know how to solve, right? Yeah, we know how to solve because, yeah, look at that, the p function, r function, right? Yeah. So if you compare with, yeah. Yeah. So we can assume, our old p function, our old r function, right? So we know how to solve it. Okay? Yeah. So after we derive in this form, then we just apply the formula. Yeah. Apply existing formula. So we can find a solution. Yeah. So this is the Bernoulli equation. Now we know we can solve any Bernoulli equation, right? Yeah. At least we can write the formula. Yeah. Yeah. Even the integral, you cannot find the formula explicit. You leave the integral formula there, still okay. Yeah. Because we know integral, if we cannot find a explicit function as the integral result, we can use a numerical value to calculate, right? Yeah. Integral, there are several versions of numerical formulas. Yeah. Like Simpson formula, yeah. Several numerical approximation formula on integrals. Yeah, we don't worry. Yeah, we can use computer to calculate the integral. Okay? Numerically. Yeah. All right. So we treat, if you can write a formula containing integrals, yeah, it's okay. Yeah. Because you can find the final solution. Yeah. All right. Yeah. So we have we can solve all the questions in this form. Yeah. All right. Yeah. Next, let's look at a special Bernoulli equation here, because this one is very useful in the real world. So we take it out. We want to study a logistic equation, a special type of Bernoulli equation, logistic equation. Logistic equation has this form. Y prime equals capital A times y minus capital B, y squared. In Bernoulli equation, that little a equals 2 here. That little a term, y to the a, here y squared. Yeah. So that's the special case of Bernoulli equation. Yeah. But this equation has a very interesting model, so we will see. Now, it's a good model for the real world, many real world problems. Yeah. Now, the constant a capital AB not equal to 0. Yeah. Solution. Yeah. Bernoulli solution, right? Yeah, so tell us using this substitution, u equals y to the negative first. Yeah. Then u prime, yeah, and y prime, yeah, you update equation, you get a u prime plus capital A u equals capital B. Very simple, okay? Yeah, very simple, yeah. And this one is a separable ODE. So we can use separable ODE to find its solution, right? Yeah, yeah. Although you can also use that way. Yeah, you can use that way, but also separable way you can find the same solution. If you use that way, yeah, we just derived, yeah. So you find x, h, capital AT, and then u, yeah, in that way. So you write that u, yeah. But the y is the reciprocal of u, so right, yeah. So that integral is easy to calculate. Yeah. So you have that, okay, all right, easy to calculate. Yeah. But the y is the reciprocal of u, so you write y equals 1 over the denominator. Yeah, that one. Yeah, that one. Yeah. So if you can further write in this way. Yeah. Capital A, capital B are given constant, are given non-zero constant. Yeah. At the beginning, we assume capital A, capital B both non-zero. Okay. Given non-zero constant. But this little c is a constant. Yeah. This little c is a constant. You can change. Yeah. Every time you choose one specific little c, you get one solution we call a particular solution. Yeah. So c equals one particular number, then you get one particular solution. Yeah. With that c there, we call a general solution. Yeah. So here there is a concept here. So this is this version containing c we call a general solution. But if you select constant number for little c, concrete constant numbers, then you get a particular solution. Okay? Yeah. Particular solution. For, let's say, C0. Okay? So you select the constant C0. Yeah. Solution. So general solution, particular solution. Yeah. All right. But there is another special solution for this equation. Yeah. Another special. If you look at the original equation, can you see y equals 0 constant? Is it also a solution? Y equals 0 all the time, everywhere. Yeah. Left-hand side, y prime is 0. Right-hand side, a times 0 minus b times 0, also 0. Yeah. So it's a simple, trivial, easy solution. But the interesting thing is, this y equals 0 solution, you cannot get from this general solution. Okay. No matter what c you choose, this y can never be 0, right? Yeah. numerator non-zero, denominator cannot be 0, right? Non-zero over non-zero, you cannot get 0. So that means this y equals 0 can never be one of the particular solutions. Yeah. So for that solution, y equals 0, because it's so special. Yeah. It's not a special case of the general solution. So we call it a singular solution. This is a singular solution. So here I introduce the concept. Yeah, singular. What's the meaning of a singular solution? Yeah, that's the meaning. Okay? Yeah. Singular. All right. Then, yeah, some comments. Yeah. Because after we solve this logistic equation, we want to see, yeah, so here, yeah, y equals 0. But here, yeah, all right. An application of logistic equation. Yeah, this logistic has some very special, important application in the real world. Yeah, so what's that? Modeling population growth. Population, okay? Population of animal, of human, yeah, population, okay? Yeah, we use this logistic equation as the model. Yeah. Okay, yeah, so let's take a look. Yeah. But when we use that population growth, yeah, we modify that. Yeah, so this version actually you can see equivalent to that version. Yeah. So let me connect these two versions. Let me connect these two versions. Okay. They are equivalent, right? Yeah. So if you compare, they're equivalent. So capital A, capital, yeah. Here, little r, capital K, you treat as constant. Okay. Little r, capital K, you treat as special constant. Yeah. P, population. Yeah. So that's the y, right? P, capital P, population. That's the y. All right. Now you can see the logistic equation, the original form. Yeah. But in order to model the population, this form is better. This form is better. Yeah. Let me tell you why this form is better. Yeah. This special form, when you describe population, yeah, for human, yeah, let's say for human, yeah, this one gives us better understanding. Because we need to do interpretation, right? When we have equation, model, we need to do interpretation. Yeah. If we use the original logistic equation, it's hard to do interpretation on population. What's the meaning? Okay? What's that meaning? Yeah. But if we use this version, then there is some very nice interpretation. Yeah. Think about it. Let's consider. Yeah. So we can use human or animal, something. Yeah. All right. So, yeah. At the beginning, we know the population increasing, right? Yeah. At the beginning, increasing, and there is a model exponential increasing. Have you heard about it? At the beginning, so the animal or human, the increasing rate is exponential. At the beginning. Yeah. At the beginning, because the total number of people, small number, relatively small, okay? You have plenty of resource, right? In the world, you have animal or people, you have a lot of resource, but the number is very small. So you have a lot of resource, so then grow exponentially. Yeah. But when the number becomes more and more, then people need to fight for resource, right? The animal also fight for resource. Yeah. Then there is a stopping factor, okay? Stopping factor. Their minus term is the stopping factor, okay? At the beginning, this minus term, the fact is very small, okay? So if you ignore the minus term, the solution is an exponential function? Yeah, right? our decay model, right? But this time A is positive. So it's an exponential increasing thing, pattern. But when your y becomes larger and larger, then there is a stopping factor. You need to add that minus term, okay? Minus b times y squared. And here we use this form. You have stopping term, okay? Yeah, here. So then, from this equation, this form, you can see the population, larger, smaller, then there is a solution, you know, there is some solution. There is a line, people call the equilibrium solution. Equilibrium solution. Yeah, think about it. So here, look at this. This K actually gives us equilibrium solution. So what's that? Yeah, let me explain that meaning of this equilibrium solution. All right. When capital P is smaller than K, okay? P is relatively small, smaller than that equilibrium solution. Yeah. Then P over K is less than 1, right? Yeah. So 1 minus a number less than 1 is a positive. Yeah. So then this differential equation is a positive term, right? Positive. Yeah. So because everything at the right hand side is positive. Derivative is positive means increasing, right? So when P is less than K, P is growing. The population is growing. Yeah. All right. Now, if P passes that capital K, equilibrium solution, past that line, then capital P over K is greater than 1, right? Yeah. So 1 minus a number greater than 1, then this big parenthesis becomes negative. If it's negative, when the derivative is negative, decreasing, right? So after the population passes that equilibrium solution line, then it becomes reduction, okay? Reducing. So back to equilibrium solution. Then going down, up, okay? So you get like perturbation around equilibrium solution. How about that? So this model gives you that, you can explain that phenomenon, okay? That phenomenon. Yeah. On population, okay? Yeah. All right. So let's stop right here. Yeah. So we finished the module part of module 1, the whole module 1. Yeah. So next time we will start module 2.